Just invite the marching band through.
So, yeah. Let's call them up. Guys, Dr. Kim needs us.
I don't think somebody who's in a different section of algebra is just going to show up for fun to another section.
My friends would.
That was the thing we did as undergrads all the time, was we would like go to our friends, we just go to our friends' classes.
Well, because some of them have you for UWO and high school, so I feel like it's fun.
Actually, one of the things I try to do every semester, I'm a crappy guitar player. I mean, like, really bad, right? But I usually take a popular song and write some math lyrics to it.
Oh my gosh.
And do that for the class. I usually dress up that day, like in a shirt and tie and all that business. Maybe that will happen.
Can you ask your Coziac to accompany you?
Sure. And then you're also saying, like, yeah, that better be the same day there's soup or whatever, but let's not go there. I'd like to just take a moment to remind you what a polynomial function is. We've dealt with these, and we're going to now look at a little twist on that. A polynomial function is a function of the form f of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus so on and so forth. These dots, I call them pattern dots. And then let me write down the last three terms. You've got a sub 2, x to the 2, plus a sub 1, x to the 1. I don't write the to the 1, though, because x is x to the 1. Then plus a sub 0 times, normally x to the 0, but I don't need to write x to the 0, because x to the 0th is just 1. So we've seen these things, and the thing is, the whole point of the dots and so on is that we don't know how long this is. This depends on what number n is. The bigger n is, the more of these terms there are. But what you do is you just keep reducing the exponent by 1. So you have n, then n minus 1, n minus 2, and so on. Today, we're going to look at rational functions. A rational function is a function of the form f of x equals, and now we have a fraction. The top of this fraction is the numerator from before. It's a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot. Just to save a little space, I'm not going to write that term, just the last two terms, a sub 1 x plus a sub 0. The bottom of this thing should also have that similar kind of look, but I want to start with a different number here other than n. So, and I'll use b's instead of a. So it's b sub k, x to the k, plus b sub k minus 1, x to the k minus 1, plus so on and so forth with these pattern dots. B sub 1, x plus b sub 0. I do have a handout if you... This is what it officially is, but this is a little confusing. So I want to just be a little informal by drawing arrows to these and saying what these really are. So on top, you have a polynomial of degree n. This is just what a polynomial of degree n looks like. That's the form. And then on bottom, you have a polynomial of degree k. And this is a typical format. The books have something like this because there's a level of care to try to say, look, n and k can be different or they can be the same. Doesn't matter if they're the same or different, but we're allowing both possibilities. And so in quick summary of what is a rational function, in just words, I think this is helpful. In other words, a rational function is a polynomial divided by a polynomial. And on the handout, you have several examples of these. What I'd like to do is just take a moment, maybe right on this sheet, I'm going to write right here. I'd like to just talk about the domain of f. To find the domain of f, we're not worried about square roots here. It's just that the denominator shouldn't be 0. So we should be avoiding x squared minus x minus 6 equals 0. Yes? We just need to avoid that. And so this should factor. I believe it's x minus 3 times x plus 2 equals 0. So in the domain here, the only numbers to avoid are -2 and +3. Those are the only numbers to avoid. All of the real numbers work. So what's the domain? In interval notation, -infinity all the way up to -2 parenthesis union parenthesis 2, -2 comma 3 parenthesis union 3 to infinity. I hope that looks all right. Just avoiding two numbers, avoiding the number -2 and avoiding the number +3. The next one, if we're looking at domain, you can do the same thing. For domain of k of x, you can say, you know what, we've got to avoid x squared plus 3 equals 0. It turns out that the only solutions you get are complex. Another way to think of this is, look, x squared is going to be positive. If you throw in a real number for x, you square it, you get 0 or a positive, and then you add 3. So the denominator here is never going to be 0. If the denominator is not going to be 0, we have no concerns for this one, so the domain is actually all reals. What about this next rational function, s of x? What is the domain here? Negative infinity to 3, 3 to infinity. It's real common for people to say, when I ask domain, they just say 3, but it's actually all real numbers except the number 3. Well, we'll stop with domain calculations here, but this leads up into the following. I'd like to ask you to take a moment to graph this function s of x. It's just from the sheet, but it's x squared minus 9 all over x minus 3. And the way I want to graph this is through an exploration. This is the first time we're graphing a rational function. So like with other times when we're exploring, a t-chart is appropriate. I'm going to suggest you use the following values of x. 0, 1, 2, 3, 4, 5. Let's do the first one together. When you plug in 0 for x, the top is, let's see, 0 minus 9. Negative 9 on top, 0 minus 3. Negative 3 on bottom, so negative 9 divided by negative 3 is positive 3. And so I can plot the point, x and y axes here. I can plot x equals 0, y equals 3 is just up here above the origin 3 units up point. But I want you to plug in 1, 2, 3, 4, 5, and see what you get. Now each time plot a point. If you'd like to work with someone, that'd be awesome. You can move, but you don't have to. So plug in, get a y value, plot a point. When you plug in x equals 1, I think you get a really nice clean number for y, no fraction or anything like that in the end. When you plug in 1 for x, what'd you get for y? 4. Okay, 1 comma 4. So 1 unit east and north of the point that's already drawn in. What about when you plugged in x is 2? What was y? Okay, so again, 2, 2, and then 5. One more tick mark, should be right there. When you plug in 3, something a little strange happens. Depends on how you're thinking about it, but I want to go through this one together. When you plug in 3, 3 squared minus 9. The top is 0, and the bottom is 0 as well. So then the question becomes, wait a minute, what is 0 divided by 0? It's not 1, because the zeros don't cancel like this. It's not 0, it's undefined. So the thing is, the rule that takes precedence here is whenever you divide by 0, you don't have something defined. So that's the thing that counts first. So we actually don't get anything. You can write undef or undefined or something like that. And then when you plug in 4 for x, I believe you get 7. And then when you plug in 5, I think the y value you get is 8. So we'll actually get like points here, but there's this like little noticeable gap when x is equal to 3. If you asked a computer to graph this, of course, the computer is faster and can pick like 2.2 and 2.3 and plot in a bunch of points. Usually the picture drawn by a computer or calculator is a little deceptive. When drawn by hand accurately, you actually get a graph that looks like. So you get what looks like a straight line, and in fact it is almost, except one point is missing. You have this diagonal line of slope 1, and if an ant were to crawl along this thing, because of this hole here, the ant would just fall through. That's okay, but ants are tough. Now this is what it looks like a hole, right? So it's drawn here with this open circle like we've done in number line diagrams to indicate that point is not there. This is a hole, and that's the technical name of this thing. Okay, this is a hole. Let me just do that. And now write down, I want to say a couple things here. First off, look back at our domain calculation. X equals 3 is not in the domain. Is not in the domain of s of x. That's what we just computed. The domain was all reals except 3. So it makes sense that when you go to this vertical line when x equals 3 that you don't get a point. And so we have this open circle to mean we don't actually have a point there. We just have everything leading up to that point. X equals 3 is not the domain of this function s of x, and there is a hole. And there is a hole in the graph specified here at x equals 3. There is a hole. The word hole is not just being used informally. This is the technical term for it. It's a hole. I'd like to write down, for now, you'll see a number of facts stated without all of the reasons why. We have to go back and revisit that a little later. But I'd like to write down the fact about finding holes. So if f of x is a fraction like this, g of x over h of x, I want to pause for a second. By g of x, I just mean, if that's the numerator, that expands out and can look like this. It's the polynomial on top of degree n. H of x here, I mean, that's just a shorthand way of writing this whole polynomial on the bottom. So if you have f of x equals polynomial over polynomial, the polynomial g of x over the polynomial h of x, and the x value is a root of both g of x, h of x. I want to let you know that you've got to be real careful here, and I've tried to be very careful myself. There are three functions in play. There are three functions on the board. We've got g, which is a polynomial, the polynomial in the numerator. You have h of x, which is also a polynomial. That's the thing on bottom. And then you have f, which is this thing when you divide the two. There's g, h, and there's f. So to be clear, we're talking about a root of the top, root of this polynomial on top, root of the bottom, and then the overall function, which is when you divide the two, will have a whole. Okay? We were not going to say that g has a whole or that h has a whole. G and h here are roots. And we see this example back here. 3 is a root on top. The 3 is an x value that makes the top 0. 3 is a root on bottom. It's an x value that makes the bottom 0. And so that's why f, or in this case s. I'd like to look at another example though. The example we'll stick to for most of the day is this first function on your sheet. So let me write it down. F of x plus 2, all divided by x squared minus x minus 6. And here's the thing. In this polynomial, in this rational function, the thing on top is this polynomial. Let me write down x squared. That x squared plus 3x plus 2, just that part alone, is my g of x. And it turns out that this polynomial has x equals -2 as a root. You can check. In other words, go ahead and plug in -2 for each x. In addition, that same x value is a root of the denominator. So x squared minus x minus 6, that's our h of x here. H of x, or x squared minus x minus 6, has x equals -2. And so because this x value c is a root of g of x, root of the top, and root of the bottom, so we conclude that f has a whole at x equals negative. A little later, not now, we've got to do a couple other things for the overall view. A little later today, we'll talk about how to graph. So there's fact 1 and an example. To get the overall view though, I'd like to look at the next fact. Fact 2 and an example. Fact number 2, if f of x equals g of x over h of x, and the x value c is a root of g of x, that's the polynomial that's on top, but not of h of x, that's the polynomial on bottom, then f has a 0 or a root at x equals c. This pen is running out. Wow, this is going to be fun. Example? Is that visible? I don't have much choice. It's that or, well, okay. I don't want to cut my finger. Never mind. Okay, so if you have an x value, that's a root of the top. So the x value, if it's a root of g, but not a root of h, then it's a root of this function called f. F, by the way, was, remember, g over h. So I'd like to look at an example. Same function, f from over there. Look at the numerator, x squared plus 3x plus 2. That's our g of x. This function has, this polynomial has x equals -1 as a root. I'm not verifying this right now, but if you plug in -1 for each x, overall you'll get the number 0. It turns out that x squared minus x minus 6 does not have x equals -1 as a root. Again, you can check. I'm sparing you the little calculation. But if you plug in -1 for each x, x squared minus x minus 6 will be a number that's not 0. Exactly. That's what I mean for root or for 0. I mean that when you plug in that x value, do you end up getting the y value to be 0 or not? So because you have -1 as a root of the top, but is not a root of the bottom, we fall into what this fact addresses. And so we say that then f has a 0 or a root at x equals -1. Okay, fact number 3. So there's fact and example, here's fact 3. If f of x equals g of x over h of x, and the x value, well, what do you think? How's this going to have to end? We had fact 1 over here. We have fact 2. What's going on? The type of function we're looking at is polynomial divided by polynomial. We've studied we've come up with a saying for what happens when that x value is a root of top and bottom, of both the top and the bottom. We've come up with something to say about when you have an x value that's a root of the top but not of the bottom. I think the third fact is going to address. So root of the bottom, but not a root of the top. But specifically not a root of the top, because if it's a root of the top as well, this is covering it, this both. So we should have now a fact that talks about if the x value c is a root of the bottom, is a root of, in this case, h of x, but not of this thing in the numerator, g of x, then the function has the vertical line x equals c. Emphasis on the x equals, so I'll throw this in a box. Not just c, but x equals c. It has the vertical line x equals c as a vertical asymptote. A vertical asymptote. Example. So same function. The top was x squared plus 3x plus 2. The numerator, by the way, does not have x equals 3 as a root or a 0. You plug in 3 for x, and x squared plus 3x plus 2 is not going to be 0. However, the denominator does have 3 as a root. So that denominator was, again, x squared minus x minus 6. This has x equals 3 as a root. So we fall under this third fact. Root of the bottom, but not of the top. And so the conclusion here, so the line x equals 3 is a vertical asymptote. Let me summarize what we have over here. I want to keep the fact up. I'm going to do the following. What we have for this function, let me write it out in full. The function we had here was f of x equals, and then the fraction as follows. It was x squared plus 3x plus 2 on top. On the bottom it was x squared minus x minus 6. And if we summarize the 3 facts we have, this function has a hole at x equals -2. That was here. Right? That thing is heavier than it looks. This, shit! I just I'm recording, and now that's going to be in the YouTube video.
That makes it 10 times better.
Okay. I've avoided saying anyone's name today for that reason. Okay. All right. And then this thing has a 0 at x equals -1. That was what we just had over here, right? Instructor fail. And then finally, the fact that we had over here was that the line x equals 3 is a vertical asymptote. So this function has x equals 3 as a vertical asymptote. Well, what I did, oh, come on. Was I graphed the function, and I'd like to first take a look at that hole. If you zoom in, calculators, Desmos, all of these things are a little deceptive because it looks like the graph goes through and has a point here. What gives? But if you click and you ask for coordinates and you go up to -2, did you see it? Undefined. But the other thing is, if I just move the mouse cursor right, you see that the hole is actually drawn in by the system now. This is the drawing I wish that Desmos gave in the first place, right? There should be this very obvious hole right there, because this is how I would draw this to not be deceptive if I'm really drawing the graph. There's a hole there. Okay, we verified that in the picture. 0 at x equals -1. Remember, 0 is really an x-intercept, and you see it right there, x-intercept. The last thing is, x equals 3 is apparently a vertical asymptote. I zoom out, and it sort of does appear like that, but I can do even better. I can draw in blue, that green, that vertical asymptote. Right, you see how this red function is veering, and then just barely missing this vertical asymptote. That look all right? Okay. What I'd like you to do is work together on the following function. So find the holes, zeros, and vertical asymptotes of UWL of x. Last function on your sheet. It looks like a beast, but the fact that it is factored on top and bottom makes it actually much nicer. So first talk about what are the holes, zeros that are common on top and bottom, and then go from there. Maybe I can edit the audio it?
Please don't. Too much work.
Don't?
Please
Nobody cares here.
don't.
All right, so you have all three facts here on the board. One of these days I'll figure out what I'm doing. Not yet. No. Don't draw it. Don't draw the function. There's too many things going on. Yeah, we have a lot of things to discuss before actually drawing these. First off, what holds at which x values? 7 and 12. Are we in agreement there? That these are the only values of x that make the top and the bottom 0. Okay. What about zeros? 2, 6. Everybody okay with that? I don't have the sheet in front of me. I'm just. What about vertical asymptotes? So these are x values that make the bottom 0, but the top has to be non-zero. 1, 8, 9. And let's verify this, shall we? We got Desmos. I've already pre-typed in the function here. And let's turn this one on, see what this looks like. That's kind of fun.
Oh, what the? Oh,
Yeah. There's like some other little stick of this down here. There's a lot of things going on. But we can verify. This hole at 7. 6, 7, right? Oh, come on, computer. Oh, I have to go that way. Hole at 7. Okay. Hole at 12. Scroll over that way. If I'd only move the correct direction. There's a hole there. Zeros at 2 and 6. That's a little easier to visualize. I'm just going to zoom in. You see that the graph crosses the x-axis here at 6. The graph also touches the x-axis over here at 2. And those are, just like the discussion we had with polynomials, those are the only place where the graph touches the x-axis. I want us to emphasize, these are the only places. So it appears like the graph is touching the x-axis here if you zoom out, and it's not. The graph is just getting closer to the x-axis. The only places the graph truly touches the x-axis is at 2 and at 6. Everywhere else, like right along here, this is like those car rides with siblings. I'm not touching you, right? That's all that's going on there. All right. What else? I'd like to verify vertical asymptotes. If I just zoom out, I think you'll see a vertical asymptote here at 1, another at 8, and another at 9. Okay, you can sort of visually see these. How are we doing so far? Okay. I'd like to summarize what we've seen in the form of a Venn diagram. Some of you will find this helpful. But the three, and some of you are like, well, I'm okay with the 3 facts. But here's just another way to put it all together. So here's a summary of what we have so far. So consider just for a moment one x value. Yeah, we look at many, many different x values over the course of one of these problems, but I just want to talk about one number, one x value called c. And we have a function, f of x, that looks like this. It's g of x over h of x. And my Venn diagram has these 2 circles, with this circle over here on the left representing x equals c is a root of the top. And the top, I'm just writing g here. I think it's very important, since you've got an f, g, and an h, that we're clear about which is which. So we're talking about a root of the top of this g of x. Over here, this circle on the right is x equals c is a root of the bottom, and I'll just write h. The first thing we looked at, fact 1, was what happens when you have a root of both the top and the bottom, and we had a hole for f. Again, I'm going to be clear to say that then f, I think it's really important here to mention that we're talking about f has a hole. It's not g that has a hole or h that has a hole. Fact 2 we looked at was when you have a root of the top but not of the bottom. So that's over here. And in this case, then f has, or a 0, if you want to call it that, at x equals c. So a root of g turns into a root of f as long as that number c is not a root of h. See, it's outside of this circle. And then finally, when you have a root of the bottom that's not a root of the top, so inside this circle but outside the circle on the left, then we saw that f has the line x equals c. BT dubs. When you're dealing with zeros or / roots, holes, and vertical asymptotes, I want to note the following. I think a key tip is that it is easiest. What's going on if you the top and bottom. Although we dealt with this fairly innocent and tiny function f, it was actually a little difficult to see what was going on there. Whereas when I asked you to work with UWL of x, that wasn't so bad because it was in a factored format. So check this out. I did this intentionally so that we can talk about, so you can really feel out why this is true. You were originally given f of x was the following function, x squared plus 3x plus 2 all over x squared minus x minus 6. Okay? That was on your sheet. This is the example we've been working with. And it's actually much easier to use f of x equals the following. And in a factored format, it looks like this. Quantity x plus 1 times quantity x plus 2, all divided by quantity x minus 3 times quantity x plus 2. It's much easier to start with this and say negative 2 is a root on top and bottom. That's where there's a hole. This factored form is a lot easier to deal with when you deal with roots and holes and vertical asymptotes. What I'd like to do is talk about how one would go about graphing something like this. To graph this, there are three considerations. There are three things we have discovered so far. We saw that there was a hole of f, x equals negative 2. We saw that there was a root of f, x equals negative 1. And just to emphasize, I already did say something like this, but I just want to say that negative 1 in x-intercept, but the emphasis here is negative 1 is the only x-intercept. Only x-intercept. So when you graph f, there's only one place the graph may touch the x-axis, and that's at x equals negative 1. And then finally, the third thing we saw was that there was a vertical asymptote of f, which was the line x is equal to 3. So I want to take a moment to describe one at a time, how do we actually now plot a hole, a root, and a vertical asymptote. The first one, is, I'd like to pick on the easiest one, which is the root. The root, I think, is easiest because what you do is, a root, recall, a root of f is when you graph the function, that's an x-intercept. So all we do is, we move 1 unit over on the x-axis at negative 1. There's a point, and the graph goes to that point. Check. Right? We're done with the part of graphing the root. The other part's a little bit more work, so we're going to spend a little time there. I should pause. Are we doing okay? Seconds, turn a neighbor. So it's just a line. It's a vertical line in the graph. Well, it's not in the graph, but it's a vertical line that if you draw into the graph gets closer and closer to this. I'd like to talk about graphing a hole, because that's one of the weirdest things that we do. This is not so bad, but I think it requires the following explanation, and it won't be too bad. How do you go about graphing a hole? It sounds like the process ought to be simple. There is one little detail, and so here's a very common question I get. You might ask me this question next week. Totally fine. I expect to hear this question, but I want to address it now. Bring it up again, that's fine. But the question that comes up is, where do I know, or how do I know, oh, this is poorly worded here in my notes. I'm just going to write it down. Where do I know where to draw? This is, I didn't even realize this. That's grammatically awful, but we'll just go with it. Okay? Where do I draw the hole? Okay, there's a hole, and we saw an earlier example with a t-chart for that function s of x, but using a t-chart is, in general, not going to work out. It's going to be too messy. So there's a different method that's actually much cleaner. And here's what you do. Once you are certain. So the thing is, the hole, in this example, we know that there's a hole when the x-coordinate is negative 2. But when you draw a hole, that's actually a missing point in the graph. So then you're asking, like, where on my paper do I draw that hole? I know the x-coordinate is negative 2, but what about the y-coordinate? Like, where exactly do I draw that hole? So to address this, once you are certain, and this is key, once you are certain there's a hole, at x equals c, then here's how you find the y value. Okay? Again, we already know for this function, we already know the x value of the hole. It's negative 2. We just don't know where along that negative 2, 1 unit over from this x-intercept, where along here are we supposed to draw that hole? And what you do is this. You cancel your factors. Cancel your factors, factor or factors, sometimes plural, of x minus c on top and on bottom. The reason this even makes any sense is you have to have a factor of x minus c. In our case, if you don't have a factor of x plus 2 on top and bottom, you didn't have a hole. There's no way, you have to have at least one factor of x minus c on top and bottom. So we cancel to create this thing called the reduced function, and you plug in this value of c into the reduced function, to this thing called a reduced function. Overall, that's the recipe, that's the method. But I'd like to look at an example. Our example here, make more sense of it. So in our example, f of x is equal to, and I'll write it in its factored form from over there, x plus 1 times x plus 2 all over x minus 3 times x plus 2. So once you are certain you have a whole, right? So don't cancel too early, because if you cancel early, it's really tempting in these, by the way, to just cancel the x plus 2's right away. If you do so, you will not detect the whole that is here. So once you are certain that you have a whole, like -2, then you cancel. But I don't even draw cancellation lines here. What I really do is just after the cancellation occurs, I have a reduced function, which I'm going to call r for reduced. And my reduced function has the effect of the x plus 2's are canceled, so you're left with x plus 1 over x minus 3. Get what I'm doing here? I'd rather you not even draw these slashes in because it creates a misconception. It's just once the cancellation of x plus 2's is done on top and bottom, you get this thing called the reduced function. And now all we do is step 2, plug in the value of c. Our value of c is -2. R of -2 is equal to -2 plus 1, or -2 minus 3. In other words, -1 over -5. The negatives cancel, we simplify. That is the y value of the whole. The whole is -2. Y value of the whole is positive. I could very well draw on that picture, but I think it's helpful to say, look, after that work, what I'm going to do is Control-C, Control-V, that thing over here. Or if you're on a Mac, Command-C, Command-V. Okay, so we had that x-intercept already drawn in. And then at -2, 1 unit over to the left of the -1, we're going to draw a hole. And the question has always been, like, where? And now we know that that hole has x-coordinate -2 and y-coordinate positive a fifth. So right here, that's my 1/5. And then there's a, looks sort of like 0 is sort of floating around. So just maybe I'll just comment here that this is the hole in the graph. Take a moment then to talk a bit about graphing a hole. We need to talk about graphing a vertical asymptote. The thing is, it's a little too strange. I'd like to look at a simpler, much smaller example. So we're starting a section on how to graph vertical asymptotes. Eventually we can go back to this question, but I want to just start off here in a kinder setting by doing this as a group. So let's sketch the graph of c of x, a function now called c. It's 1 over x minus 5. And I'd like to graph this near the x value of 5. C of x equals 1 over x minus 5 near the x value of 5. Oh, I should state that 5 is a root of the denominator. 5 is a root of the denominator, but not a root of the numerator. You plug in 5 for x, and while the bottom is 0, the top is not 0, the top is 1. And so that means we do have a vertical asymptote. X equals 5 is a vertical asymptote, this function called c of x. How do we graph a vertical asymptote? This is sort of the one key place I want to get across the idea that t-charts are always going to be the way we graph a vertical asymptote. So what I'd like to do is start by picking numbers for x that are close to 5 but not exactly 5, such as 5.1, and then 5.01, that's my next x value, and 5.001, and 5.0001. Now we'll plug in 5.1 for x. And if I write this out, we'll write out my steps here. This is 1 over 5.1 minus 5. Or this is 1 over 5.1 minus 5 is 0.1. And if you'd like to, you can write this as 1 over... Now the 0.1 there is really 1/10, right? So you've got 1 over 10. And 1 over, by the way, means reciprocal of, right? So we've got the reciprocal of 10. Say the reciprocal of a 10th. If we look at the next x value, 5.01, we'll plug in for x again and have 1 over 5.01 minus 5, which is equal to 1 over, now let's look at that denominator. The denominator, if you had $5 and a penny, and then you lost $5, 0.01. And this is 1 over 100. And 1 over 100 is, and once you've written down 1 or 2, you'll usually see the pattern. You don't have to write the rest of these, but you'll get 1,000 and 10,000. And so if we were to graph this, get some axes down here. If I were to graph this, here's 5. Now I'm not saying we're looking at 5 exactly. We know, in fact, 5 is not in the domain. But if you look to the right and you go to 5.1, which this will be a little not to scale, but at 5.1 on x, then you get 10 for the y value. Fine, I'll just sort of plot that there. And then when you move in closer, 5.01 is closer to 5, then you get a y value of 100. And then when you plug in 5.001, the y value is 1,000. And then when you get closer to 5, and you're at 5.001, you get 10,000. It's like a point right there. what turns out to be the case is if you connect the dots, you'll get a graph that looks these arrays. But I did discover that by accident. Okay, that's what happens near 5 to the right of 5. What about a little to the left? Same deal. We can create a t-chart, x and y values. I want numbers that are near 5 but a little to the left, like 4.9, 4.99, 4.999, 4.9999, and so on. Usually you only need 1 or 2, and then you can BS the pattern here. So we plug in 4.9 for x, and we'll have 1 over 4.9 minus 5. In other words, we have 1 over negative 0.1, which will be negative 10. And your next y value, when you plug in 4.99, it will be negative 100. And you'll have negative 1,000 and negative 10,000. So same sort of deal. You go to 4.9, which is like here on the x-axis, and you get the y value is negative 10. And you move a little closer to 5, and you get negative 100 and negative 1,000 and negative 10,000, and you get. And what's going on here is we're actually seeing from the t-charts, and when you plot these points and you have these very explosive y values, you're actually seeing that the graph is really avoiding this dotted line that we draw in that is called the vertical line. I should make the following comment that should you be taking Math 175 next semester, applied calculus because your major's in CBA, or 2 semesters down the line if you're taking 207, that's calculus with trigonometry, you will be told a different thing regarding how to find vertical asymptotes. In that class, that instructor's rule applies. That method is going to use this thing called limits. We can't talk about that here, all right? This is the method you're learning here. I promise I am telling you the truth. I am not telling you the whole truth. So please, when you take calculus, you don't want to go to the calculus prof and say, but my algebra teacher said, right? This is the method that works here. There's a slightly different, there's a new take on it that sort of enhances what's going on in a calculus class. I'd like to take a moment to switch gears and talk about horizontal asymptotes. So what about horizontal asymptotes? As long as we're doing this t-charts thing, I'd like to just talk about what's going on here. And I should try to clarify that, look, for vertical asymptotes, always do the t-charts thing. For horizontal asymptotes, we're using the t-charts to just discover what's going on. So what does, our question we're discovering is, what does y equals 1 over x minus 5 look like? What does this look like when x is really big? And then on the flip side, when x is really small, but what I mean is like when x is really negative. So we'll use a t-chart to discover what's going on here. And by really big, I mean like maybe x is 100. I'm just saying maybe that's not so big. So then we'll look at like, let's say 10,000 and then maybe 100,000. So when you plug in 100 for x, don't you get the y value to be 1 over 95? And then when you plug in 10,000 for x, shouldn't you get 1 over 9,995? And then the next one just should be one more digit of 9, so 1 over 99995. But what kind of number do you get when you do 1 divided by a huge number like 99,995 bottles of... So 1 over this huge number, what kind of number are you going to get? If you typed 1 divided by 99,995 in a calculator, is that going to be a big number, a small number? Super small number, right? This will be a very small number, very small number. And if we were to graph, just to explore what's going on. So when x is 100, you get 1 over 95, which is already kind of small, right? But then when you move out more to the right for 10,000, you have an even smaller number that's closer to the x-axis. And then you move out more on the x-axis, and 1 over 9995, that's even smaller. And so in this particular example, we'll see other types of examples, but this graph gets closer and closer to the x-axis, which in this example serves as a horizontal asymptote. We can do the same thing by looking at x values such as, so in a t-chart, negative 100, negative 10,000, and so on. And so when you plug in negative 100 for x, well, you really have 1 over, so negative 100 minus 5. How about negative 105 in the denominator? So 1 over negative 105, and then 1 over negative 10,005. And here's the thing, when you compute out this on a calculator as well, 1 divided by a huge negative number is a small negative number. So you'll have the graph like that and get closer and closer to the x-axis again. What I'd like to do is have you take a look at, on the back side of this handout, there's a section here that says horizontal asymptotes. There's one last activity for the day. Bear with me here. So here, I'll leave this up for your reference. But you have that generic form of a rational function. And look, we earlier said n and k could be equal or not. Okay? And if n is smaller than k, so the degree on top is smaller than the degree on bottom, then without any computation, I promise you that y equals 0 is a horizontal asymptote. So take a look at the front side. I'll leave this side up. But if you look at the front side, what about k of x? What is n? Right? N is, by the way, the degree of the top. Right? So in k of x, what's the degree of the polynomial on top? What is the degree of the polynomial on bottom? So n is 3, k is 2. We're in this bottom case. And the guarantee here is that this function k has no horizontal asymptote. I'd like to take a moment and look at what. Do you see that fourth example? WT of x? That's not a real word, but due to memes, it basically now is. So what of x? The degree on top is 4, so that's n. The degree on bottom is 4 as well. So we're in this middle case, n is equal to k. Let me write this out, that here, what of x has y equals, and we need a sub n over b sub k. A sub n is the number to the left of x to the n. So what is a sub n here? The number in front of x to the fourth. B sub k, look at your example here, is b sub k, the number to the left of x to the fourth. So this function, what of x, has y equals 7 over 6 as a horizontal asymptote. One last, zap of x. The degree on top is 3, the degree on bottom is 6. So that's this case here. And y equals 0 is the horizontal asymptote. All right, thanks. Have a nice break.